This is the solution video for the revision question on inferential stats, and the first part of it is about farmed salmon, and we're told that the lengths of the salmon in a fish farm are normally distributed. We're given the mean and we're given the standard deviation. Now, just to point out here, this statement about normal distribution gives us permission to use our Z tables and any of the formulae associated with them. We've got a mean and we've got a standard deviation, like I said. It'll be a good idea for us to note those. And the question asks us to find the proportion of salmon which are more than 35 centimetres in length. Now, don't be put off by this word proportion here. All it means is what fraction, decimal, or percentage of the salmon fit into that category. So the value in question is 35 centimetres. We just want to know how much of the salmon are bigger than that. This value is not a mean, so I don't call it X bar, I just call it X. So to figure this out, I first of all have to get my Z value. My formula is written on the page here, and I'm going to substitute into it. And I get a Z value of 0.92. So this is what I look up then in the log tables. It might be useful for me to draw a quick sketch to kind of just orientate myself with regard to the normal distribution. I've got mu in the middle. And of course, positive Z values go to the right of mu and negatives go to the left of mu. And I want to figure out the amount of the salmon that are bigger than this Z value. But just remember that in the log tables, I can only look up the values to the left of my Z values. So I can look up the probability that Z is less than 0.92, which is 0.8212. Remember that when it comes to the normal distribution, my total is 1. So if I want to get the other side of the Z value, I'll just take my value so far from 1, giving 0.1788. So the probability that I'll have a Z value bigger than 0.92 is 0.1788. If I want to refer back to the actual lengths of salmon again then, I can say the chances of picking a random salmon that has a length greater than 35 is 0.1788. So now we have figured out that 60% of the salmon produced in the farm have lengths between two values. One of those values is known to us, 31.8, and the other value is unknown, that's T. We want to find this T. It might be useful for us originally to just take that 60% and write it as 0.6, because again, this refers to an area under the normal distribution. So when we go to look up our Z tables in a while, 0.6 is what we're going to be looking for, or some values related to that. Again, a diagram is a good plan to help us visualize this. So again, we have mu in the middle, and we actually know what this was from previously. It's 32.8. So that lets us know that the 31.8 obviously has to go to the left of that. So T couldn't be over to the left again of 31.8 because there isn't enough of the diagram. So 50% is contained to the left of mu. So that means that T is going to have to be over here on the right-hand side somewhere. And this shaded portion is the 60%. So I'm going to have to try and make Z values for both of these. So I'm going to list out the required information for both and then put them into the Z formula. Maybe to avoid confusion, I could call them Z1 and Z2. Again, not a bad idea to note the formula. And now let's fill in. So I've got Z1 and I've done what I can for Z2. So now let's have a think about this. There's a few ways of going about this. One way to do it is to figure out what space is taken up here to the left of 31.8. That's that first Z value that I'm looking at, so the minus 0.42. And when I figure that out, I find that 0.3372 of my normal distribution area is to the left of that. Now, I know that I have to have 60%, or as we said earlier, 0.6 in this red shaded region. So that would mean that up to that T, I should have this much in the blue shaded region, plus 0.6 from the red shaded region. So to the left of T, I should have 0.9372. So all I have to do now is go off and look up what Z value in my log tables corresponds to that. And when you're looking that up, look up the number that is closest to 0.9372. I'm just spotting a little technicality that I should fix. I should really say X is less than T because T isn't a Z value. Anyway, it doesn't matter. When I look up my log table 0.9372, the Z is 1.53. Now that Z value is the Z value for T. And I already started making that calculation over here. So I'm going to let this now equal to 1.53. And now just a bit of rearrangement to get T by itself. And T is 36.47 centimetres. Okay, next part of the question, they're asking us to test a hypothesis. So they're saying that things have changed in the fish farm and there's a random sample of 250 salmon that are taken from the group and their lengths are normally distributed, and there's a mean of 33.2 and the same standard deviation as before. So I'm going to just make a note first of all of this information that I have from my sample. So my n is 250, my x bar is 33.2, my s is 2.4. Notice here that I'm using x bar because that is the mean of a sample, and I'm using s because s is the mean of a sample. Now, to be honest with you, like, you're perfectly fine there to use sigma if you want, and actually this s value is going to go in for sigma in the calculation. But if you want to be absolutely spot on, s is the letter that we assign to standard deviation in a sample. Okay, so now we have to decide what's happening with our hypothesis. So we wanted to test the hypothesis that the mean length of the salmon produced has not changed. So let's think back to what was happening originally with the salmon. Originally, the salmon had a mean of 32.8. So we're going to say that HO is that mu equals 32.8. Things haven't changed. They also wanted to state H1, the alternative hypothesis. This is just stating the opposite of HO. It's just stating that that's not actually what the mean is. There's a few ways now of going about our test. So we can either use confidence intervals or we can use the test statistic, which is using the Z formula. Both of these will actually end up giving us the same result. I'm going to do this using the confidence interval method, and we'll actually see in part 2 of the question what I'm talking about for the test statistic, because I'll actually calculate that as part of the part 2. So let's remind ourselves again of how the confidence interval can look. So I've got my setup there for confidence interval, and I've got most of this information noted. There's x bar 33.2. That's the fellow I'm going to use for sigma. My n is 250. So let's put those values in. Don't forget, I'm just going to leave the sky as mu. I'm not actually going to put a value in for that. So I've just filled those values in. And when I calculate both sides of that interval, I'm going to get 32.9 and 33.5. Now, going back to my null hypothesis there again, that was saying that 32.8 was the mean. If I look at that in comparison to my interval, I can see that it's actually outside the interval. So the first thing that I'm going to do as part of my conclusion is to note that. And then that's going to inform my decision about HO. So since it's outside the interval, it means that I'm going to reject it. But notice that they do say in the question, give your conclusion in the context of the question. So I need to actually refer to the salmon and what's going on with them. So I generally start off with the phrase, there is evidence to suggest that the mean length of the salmon is no longer 32.8 centimetres. Or I could say that it differs from 32.8 centimetres if I liked. Okay, moving on then to part 2. So like I said, in part 1, we actually had a couple of alternatives of how to go about doing the question. One was the confidence intervals that we did. The other is the test statistic. In part 2, they're asking us to find the p-value of the test we performed in part B, part 1, and explain what this value represents in the context of the question. So to get the p-value, I first of all have to get the z-value. Now, in the previous questions that I was looking at, I was using a slightly different formula to what I'm going to use now. In the previous questions, it was x minus mu over sigma. But that was when I was just looking for a particular value out of the overall group of salmon. Whereas now I'm talking about the mean of the salmon. So the formula that I'm going to use this time is this z value formula, x bar minus mu over sigma over root n. So again, the x bar there referring to the mean of the sample, and I'm comparing it to the mean of the population. So I'm going to fill my values in there. I'll just note them first. So I've just noted all that information. None of it's changed since part 1. And I fill it into the formula and I get 2.64. This is the test statistic that I was referring to earlier on. Just to visualize what this value actually means, if I quickly sketch a normal distribution, it means that my result is up here at 2.64. And the critical limits that I have are minus 1.96 and 1.96. So if I'm out past those, that's kind of the equivalent of being out past my confidence interval. So my Z value is out past that. So if I'd gone about it this way, the result that I get here is out past my 1.96. So again, that would lead me to go back and have the same conclusion that I'd reject, etc. But now it's not just that they want the p-value. And the p-value is closely linked to the Z value. So on the one hand, the p-value represents the chances that if the mean of the population is really 32.8, that I'd actually get a mean this far out or further even from the mean in any given sample. And on the other hand, the p-value represents the chances that mu is correct, given that I got a sample mean this far out or further out from mu. So the way that I figure this out is I figure out the chances that I'm at least this far away from the mean. Now, it's important here to realise that this doesn't just take place on one side of my normal distribution. I have to do it symmetrically on both sides. So I also have to take the far side of the normal distribution. So in practice, what this means is I need to figure out twice the value of z being greater than 2.64. So I'm going to go to my log tables and I'm going to say that I've got twice. Now I'm looking up something to the right of a z value. So I'm going to have to use a 1 minus. I'm going to look up the 2.64. And when I work this out, I'm going to get 0.0082, which is a really small probability. And what that probability is it's the p-value. What that is in the context of this diagram is it's the chances of being in the shaded bits at the end of my diagram here. So that was the first bit. We had to find the p-value, and now we have to explain what it means in the context of the question. So we have to go back to our salmon again and our HO. And the first thing that I'm going to make a comment about is the p-value in relation to the critical value that we must compare it to, which is the 5% level of significance. I'm writing that as a decimal at 0.05, of course. And if I have a greater than 5% chance of mu being right, then I say, okay, fine, I'll take mu. But if I've got a lower than 5% chance, then I reject. So in this case, I first of all note that the p-value that I got is less than 0.05. And this means that I reject HO from part 1 of the question. And then to relate it back to our question again, we can say that there is a 0.0082, so that's less than 1% chance that the mean of the salmon is still 32.8 centimetres given the mean of the sample. And we're on to part C, last part of this question. So this time we're looking at trout. That's grand. So in fish farms, the length of the trout are normally distributed. So again, that gives us permission to use our Z tables. And we're told that 97.5% of them have lengths of less than 34.2 and 67% of them have lengths of greater than 26.6. We want to find mean and standard deviation. Now notice again in this question, they're not talking about means, they're talking about individual lengths. So we're going back to using Z value formulae, but it's the original Z value formula that we used at the beginning in part A. So it's this formula that we're going to be using. The percentages they're talking about here, we might be best representing as decimals. We're going to be looking those values up in the log tables in the Z tables shortly. And again, drawing a sketch to visualize this may help. So first of all, I've got 0.9750 below that 34.2. And we've got 0.6700 above that 26.6. Notice that I knew that this guy had to go to the left of mu because I needed more than 50% above him. So one thing that would be really handy is if I knew what Z values were associated with these. The first one's straightforward enough. I can just literally go to my log tables, look up 0.9750 or as close as I can get to it. So that's grand and straightforward. That's just 1.96, job done. This guy there's a bit more to him because he's on the left-hand side. But if I was to look up 0.6700, it would give me the Z value that had that area below it. And that would be a positive version of this guy over here. So if I go and look that up, I'd get 0.44 on that side. So I'll just take the negative version for this side. So at this stage now, I've got X values and Z values. So although I don't have mu and sigma, I do have the possibility of making two equations that contain those, and then I can start using a simultaneous equation. So let's look at how that develops. Filling in my Z formula for both of those, I get two equations. It'd be nicer, I suppose, if I did into fractions. I'm going to bring up my sigmas and multiply them. So that looks a bit better. And I suppose the easiest thing to do here would be to cancel out the mu's. So I'm going to change the signs of this guy and write him in underneath this first equation here. So off go the mu's, and I can simplify that a little bit and get sigma by itself. So I've got an approximation there of sigma being 3.17 centimetres, and now I'll just sub that sigma back in to any of the previous equations to get my mu value. I'm going to choose to sub it back into this guy here, since it already has a positive mu. And then just a little bit moving around to get mu by itself. And we come out with 27.99 centimetres. Bit of space down the bottom for the answers, and we're done.